Okay, assalamu alaikum. Let's get started. Today's lecture, inshallah, we first of all, if you have any questions about assignment 2, please let me know. Or assignment 1, if you have any questions about assignment 1, if you have to resubmit any part of assignment 1, please let me know. Okay. After that, we're going to get started on research problem 2. Today, we're not going to work on the ECG signals except for the first part, which is related to resampling of digital signals. We're just going to use the ECG signals here. And then for the remainder of the lecture, I'm going to basically introduce you to the different parts that we're going to implement for the ECG classification system. But we're going to start on simulated data. I'm not going to work with the ECG so that we can understand, at least we know the difference between the different signals, and we can change the parameters of different signals so that we can see how this will affect the result of the basically the performance of the system. So we're going to talk about basics of statistical processing of data. Okay, we're going to talk about what's the meaning of statistical features with some examples. Very simple examples, which are actually you will be surprised that you will be very much sufficient for the task that we're going to do with the ECG signals. We're going to talk about something called statistical hypothesis testing, which is actually very important to understand because actually it is basically the idea behind statistical feature selection. Okay, so whatever features we generate from the first part here, we have to actually make sure that they are relevant and they can be useful in our application to basically classify ECG signals. So basically, statistical feature selection will make sure of that. After we do that, we do signal classification or statistical classification. I'm going to just give you a very broad idea about what classification is and basically give you some examples. I'm not going to work on code related to that. I'm basically going to show you some examples for these, but not this one here. Okay? In all of these, we're going to discuss the effect of sample size. Sample size means that how many cases you have. Okay, so for example, if I have one case, can I build a diagnostic system using one case? Can I build it using 10 cases? Do I need 1 million cases to be able to have a reliable system? We're going to test that with some very simple examples. Okay, so let's start. If you have any questions on assignment 2 or assignment 1, do you have any questions? Okay, if you don't, if you need to ask questions about assignment 2 after this lecture, you can contact me and I can arrange for a meeting with you if you need. Okay. So let's get started with resampling of digital signals. Okay. In order to do that, basically, I'm going to start with the reader applications that we actually talked about last time. Basically, we have a reader, a program reader code that reads ECG signals and just plots them from the database that I gave you. Okay, and basically, we noticed that we have 4 types of signals. Normal, ventricular couplet, ventricular tachycardia, ventricular bigeminy. They have 1080 samples, okay, in 3 seconds. The sampling rate here is 360 samples per second. For the remaining signal, the 5th signal, which is ventricular fibrillation, the sampling rate here was 250 samples per second. So the question now is the following. Okay. Given, the problem is as follows, can be defined as follows. Given 2 signals, signals in general, sampled using 2 different frequencies. One, 250 samples per second, and the remainder is 360 samples per second. basically design, the required is to design a system that would make, or that makes, the sampling rate uniform in all signals. This is the required. How can we do that? Basically, the example we have for ECG signals, we have 3 seconds recordings. This means that we have, for some samples, we have 1080 samples, and the other will have 750 samples for the same 3-second duration. So basically, this is exactly the same. This is for 360 and this is for 250. What can we do to make the sampling rate uniform, in your opinion? Just give me an idea, just give me your thoughts. You don't have to give an answer. I don't expect you to know the correct answer, but just give me what can we do? Can we just basically take this and take the first 750 samples and throw away the rest? Okay, so basically take the first 750 and throw away the remainder of the 1080 samples. What can we do? Should we take this and put the sample 750 samples and then add them with zeros to be 180? What can we do in your opinion? Are these valid solutions in your opinion? Let's consider one of them. Let's consider. Go ahead. If you have an answer, go ahead. I can't hear you. Can you repeat? The voice is not very clear. Okay, that's fine. No problem. Let's just consider each one of them. Okay. Now we have, if you consider this is the sampling rate was 360 samples per second. Here, the sampling rate was 250. Okay, so basically, if consider these are the samples from whatever we have. Okay, these are the samples. Okay, from 1 to 1080. Okay. If I come and take the first 750 samples and just throw away the rest, what would be the sampling rate for the 750 samples that are here? Still the same, right? It's here. This is TS. The space between the samples here is still TS. The same exact TS that was basically initially given, from the 1080 samples. So the TS here will be 1/360. Here, basically, if you consider exactly the same situation, okay, if you consider the samples here, okay, the samples here will have basically, have here 750 and here it's 1. TS here is 1/250. So if I take the 750 from here and compare them to the 750 from there, they are not the same. Why? Because TS here is different from TS there. So it's not going to work. Same thing if we came here and added or padded this with zeros to 1080. The samples here that I'm going to have afterwards will have a very different TS from TS here. So both of these solutions do not work. You have to find another solution. Okay, this is called resampling. Okay, I would like to resample one set of samples, basic one of them, okay, to become the others. Okay, so either I take the samples that were sampled at 360 samples per second and resample them to become 250, or I can do the opposite. I can take the samples that were sampled at 250 and resample them to become at 360. Which one can be done? Let me write down the solutions for you and you give me your opinion which one solutions to make TS same. Number one, resample the samples with 360, okay, to become 250. The second solution is resample 250 to become 360. Which one of these would be a better solution? First of all, the idea behind this is the following, or basically the basic concepts. The idea is basically sampling was done properly, meaning that we can recover signal. Okay, so it means that once we can recover the signal, we can basically, once we recover the signal, we can basically resample at desired rate. Can you see the idea? If I'm sampling properly, then I should be able to recover the original signal, the original analog signal. Okay, then once I recover the original signal, I can basically recover or basically resample it at the desired rate. Okay. One very important thing, I'm not sure if we discussed it or not, but actually we have to talk about it. Basically, if we have an analog to digital converter, we have a block with analog to digital converter. We have here an analog signal. And the output here is a digital samples. Okay. Basically, if I have a rate here, a sampling rate of fs, is it okay to enter any analog signal with any fs, or do we have certain requirements for sampling? Please answer. What are the requirements for fs for this to work?
Should be the same method.
Yes, we have to have sufficient sampling, right?
Right.
We have to satisfy the Nyquist, at least Nyquist, right? So fs here will be greater than or equal to twice maximum frequency, right? Maximum, right? This is basically the Nyquist criteria. Okay, this is basically the sampling criterion. If you don't do that, aliasing will occur, and basically whatever you get from here will be basically garbage. Okay, will not basically be useful for anything. Okay, so this is a very important criteria. Okay, so basically there is a big problem with this. If you consider a very simple signal, if you have a signal that looks like a pulse, okay, can you give me the maximum frequency for this pulse? Very simple signal. What's F maximum for this? If you take the Fourier transformation, if you remember what we did in the Fourier transformation of something like this will be something like this, like a sinc function. Okay, where the sinc function, if you have a sinc function, what is the maximum frequency of the sinc function? Actually, if you look at the sinc function, basically it will continue until infinity. So basically, if you want to see something here that looks like something like this, and that's it, so that you have F maximum here or minus F maximum here, you're not going to get that. This is actually going to infinity here and minus infinity from the other side. So there is a problem. Because basically, if you use F maximum, if you use F sampling of any value that is not infinity, it's not going to work. What can we do in order for us to be able to sample that without aliasing? The thing that people do is basically try to convert this to that, meaning that I'll take the actual signal, the original signal, basically, which looks like this, and I pass it through a low-pass filter. And this low-pass filter, basically, the cutoff frequency will equal to F sampling over 2. What would be the result of that at the end? Basically, it's as if I came here and multiplied this by basically something that looks like this. So basically, I removed the parts that are here and there, and basically now I have, after I do that, my maximum frequency now will be F cutoff. Okay, so basically after I do that, F maximum here will be F cutoff, okay, which basically twice F cutoff will be the F sampling that I need. This is traditionally called anti-aliasing filter. This is basically implemented in very much all analog digital converters that are available in the market. So whenever I say that I'm going to sample with 360 samples per second, it's inherently understood that you have here a low-pass filter with cutoff frequency 180 Hertz, followed by the analog digital converter that samples at 360 samples per second. If you do that, you ensure that no aliasing will occur. Same thing for the 100, 250. If I have another system for 250 samples per second, you have a low-pass filter of what? Low-pass filter cutoff will be what? Low-pass filter cutoff. What should it be? This is a low-pass. Yes, go ahead.
125.
Exactly, right. Half of the sampling frequency. Okay, so this is also will have no aliasing. So now we have a set of signals. Basically, we have first set going through this system, and the second set going through this system. Basically, whatever I'm getting here, it has no aliasing. The signals I have, the digital samples I have, they have no aliasing. I can go back to the original signal, but actually you have to notice something very important. If I wanted to get the digital signals, now if I wanted to go from the digital signals, here you have the digital samples. If I wanted to go from the digital samples to the analog samples, okay, there is something called reconstruction filter, but actually, what can I recover from the digital samples? Can I go from here to here to get that again? This is a question. Can I recover original signal or not? Can I recover the samples here or what? Can I? No aliasing occurred.
I don't think.
Go ahead.
I don't think so. We can recover it.
Why? Actually, you are right, but the reason is very important. Basically, you apply the filter here, and then you sample whatever you sampled are samples from this signal here. So basically, what you can recover is the signal here only. You cannot recover this because basically you threw away these frequencies. You cannot recover them. Okay, how can I basically take a signal that doesn't have the high frequencies and basically sample that and recover the high frequencies from the samples. I cannot do that. Whatever I sample here, I can recover. Basically, I can recover here. I can reconstruct this. But I cannot reconstruct this because basically the low-pass filter already removed all the frequencies beyond the 125 hertz. So I can recover that. So basically, I can recover a signal here that was low-pass filtered with 180. I can recover here a signal that is basically filtered at 125. So basically, I can recover this, I can recover that, and basically whatever I recover here, I can resample at any frequency. Should I resample at 360 for both or 250 for both? So basically, what I'm telling you is we're going to take the samples. We're going to take the samples that were obtained here, additional samples, and basically reconstruct this one and this one, okay? And then basically take this and that and basically pass them together, you know, through a new sampling system, okay, at a certain frequency, okay? Certain FS for both, same FS for both. What I'm asking you, what should I select for FS? Should I select FS to be 250 or select it to be 360 or select it to be something else? First of all, let's consider something else. If I wanted to resample both to be 1000 samples per second, for example, okay? Basically, you already have samples at 360 and 250. It's easier to process only one signal rather than process both. So basically, if I consider that I have samples at 360 and resample the 250 to become 360, then I basically need to resample only one signal. I don't need to resample both. And basically, you should minimize the processing effort. There is no point actually in trying to resample both while you can resample only one. The most important thing is the goal. Let's just form the goal. The goal is basically both having same FS. It doesn't really, basically, I don't care about what that FS is, but basically you optimize processing. So basically, I resample only one signal. Rather than both. So I select FS to be either 250 or 360. And the other thing I'm going to talk to you about now is I would like to also optimize loss of information. Okay, or basically, let's just remove the optimize. Basically, I would like to have no information. Okay, so basically, the processing is very straightforward. Basically, if I resample at 250 or 360, this will basically do that. Because basically, I will resample only one. Okay? Okay, but here, what about this loss of information thing? Basically, if we go up to this part here, I applied here a filter with 180 hertz cutoff frequency. Here I applied a filter with 125, basically 125 basically hertz cutoff frequency. If I would like to sample, if I would like to resample that, basically, or at least I consider the signal that I have here, the signal I have here as information from my 180 minus 180 to 180 hertz. Information here is from minus 125 to 125. So obviously here I have more information because I have more frequencies. Here basically I have less information than this. So if I take the 180 for the signal here that was sampled by 360 samples per second and resample it to 250, then I lost the information. So basically I have to take the 180 and pass it through a low-pass filter of 125 because I don't want to have any aliasing. So basically I will have to remove a part of the information that I already have. Let me show it to you. Basically, the first solution, resample the signal sampled at 360 to become 250. The signal originally has a spectrum from 180 to minus 180. Okay? This is the original spectrum. Okay? If I wanted to sample that with an analog to digital converter at 250, then I have to put, because actually the maximum frequency here would be 125. If I have frequencies like 180, they will be aliased. So I have to put the low-pass filter, the regular low-pass filter, at 125 that I talked about. If I do that, then what I'm going to end up with is something that, like the other one, 125 and minus 125. So basically a part of the spectrum here will be lost if I do that. Okay? So it means that whatever I get here will have less information than the one that you already started with. Okay? So this is the problem. So basically, if we do that, we have loss of information. Basically, we did not satisfy the condition that we should not lose information. Let's consider the other way around. If I resample the 250 at 360, basically the spectrum of the 250 looks like this: 125 minus 125. Okay. If I wanted to resample that at 360, okay, 360, the maximum frequency I allow is basically 180. So basically, I don't even need a filter here. So I'll just take the signal right away as it is, without any change, okay, and resample that basically to get the new samples. So here, there is no loss of information. I basically kept the signal that has more information and resampled the other one without any loss of information. Basically, the samples that will come out here will have a maximum frequency of 180, but actually this part here will be zeros. But actually, the original information I have was only this. I kept it as is. So basically, this solution will make much sense. You can do both actually, but if you do that, you will have some loss of information. In order for you to be, when you're trying to classify signals, you don't want to basically lose some information because actually this information might be important in the classification process. So you don't want to do that. So it makes more sense to resample the 250 to become 360. So basically what we should do is take the samples that are 750 and enter them to a resampling block and basically come up with 180 samples on the other side. Here the resampling will basically give you the samples at 360 samples per second. we're not going to be able to do that realistically. We're not going to generate the original signal and then resample it. You can do that very simply. Actually, in MATLAB, there is a function called resample. Let's look at the help for resample and see how we're going to use it. Very simple. Resample X, the signal, P and Q. Basically, you're talking about the P is basically this is the original sampling, or basically you want to resample using P over Q. Okay, so basically, let me see where the definition of P here. Okay, so F sampling is 60 here. It should be actually. Okay, basically you resample at a uniform resampling at P over Q times the original sampling rate. So if I start with 250, samples with 250, and I would like them to be 360, then I would like to resample by a rate of 360 over 250. So I put here 360, I put here 250. Let's try it. Basically, this is the same program that draws the learn data 2 samples. Let me select one of them. Basically, I'll just take one of these. This is the sample that I'm drawing. And basically, do here a resampling. Let me save that first as a new. Reader. Resampler. Okay, and let me put that lecture 7. Okay, so basically this is the resampling part. So I'm going to have X equal to this. This is the original signal that I have. Okay. What I'm going to do is X resampled XR will be equal to resample of X and 360 and 250. The original sampling rate is 250. I'm going to resample by a rate of 360 over 250, meaning that I'm going to, as if I'm multiplying the original sampling rate by this factor. It's easier to understand if you think that this is the new one, this is a new sampling rate, this is the old sampling rate. Okay, so I'm going to basically have another figure. Actually, instead of doing that, I'm just going to do, hold on, actually it's not going to work because it's not the same sampling. I'll probably just have another figure. So I have figure 3, and I'm going to draw here the XR, okay, and just gonna write here resampled ventricular fibrillation ECG. Okay, so now we have here this signal here going from 0 to 750. We would like to see that this same signal comes out from 0 to 1080. If this happens, then we are successful in doing that. So let's try it. See now the outcome. Let's compare these two. Let's just put them together. Do you see any differences? Actually, there might be some slight differences here, but actually it doesn't matter. Basically, just exactly the same value. Basically, this looks exactly like this. If you compare them, they look exactly alike. And this goes to 1080. This is to 750. It's exactly the same signal, but resampled at 360 samples per second. Okay, So what we need to do is basically we need to do that because if we want to compare the different samples, the different types of conditions, card conditions, we have to be able to have exactly the same sampling rate. Otherwise, I will not be able to. If you're given two signals with two different sampling rates, you cannot compare them. So you have to basically have all the samples, using the same sampling rate before you can proceed and basically start thinking about how you're going to compare them. Is that clear? So basically, you can use that without any problems. Actually, maybe you can try also, if you want to try the other way around. This is the example, 250 to 360. Okay, samples per second. I'm going to try the other way around. I'm going to try from 360 to 250. So I'm going to use one of the samples here. Maybe I'll use the first one, the normal one, so that we can know it, how it looks like. So basically on data 1 to resample here, I'm going to have the other way around, 250 to 360. Actually, it's the other way. So basically, I'm resampling from 360 samples per second to 250 samples per second. So basically, here this is normal. Resample normal. I have here figure 4, so that we can compare it to the other one. Okay, compare this one here to this one here. You look the same, right? But here it's 1080, here it's 750. Okay, look actually very close together. They are not. You cannot really see much difference between the two, but actually they are resampled. Okay. So you can do both, but actually it's preferred if you use the resampling from 250 to 360, because in this way you're not going to lose information that were contained in the 360 samples per second samples. Okay. And also maybe because of our data, we have only one type of ECG conditions, basically that has 250, and you have 4 types that are sampled at 360. So basically, if you want to go from 360 to 250, you have to resample 4 types of signals. You have to sample the normal, the tachycardia, the bigeminy, the couplet. The other way around, you have to resample only the ventricular fibrillation sample. It's up to you, basically. So all we have to do before we use the data in order to get started on the process of comparison is basically convert, or basically making sure that all samples are sampled at the same rate. Okay? Regardless of what you choose, I will leave this choice to you. You can actually choose to have another frequency if you want to. Okay? But actually, the optimal is to use one of the frequencies so that you minimize the computations that are needed. The second is to use the higher sampling rate because you don't want to lose information. If I have 4 types of samples or 4 types of ECG signals, okay, that were sampled at 360 samples per second, I have 10,000 or more than 1,000 samples for each. Basically, if you reduce the number of samples, you're losing information. And you're not sure, basically, if this information would be important. So it's probably better if you keep the information. But basically, it's up to you. You know the theory behind resampling now and how to do that? It's very simple, just a simple line, but actually have to understand where it's coming from. Do you understand it, or do you have any questions? Any questions? So I assume that you know now. Go ahead.
It's okay. It's okay. Clear.
Okay. Okay. So let's go back and basically start talking about statistical data processing. Okay, I think that we talked about in the beginning, at the beginning. Okay, basic statistical processing of data. I'm going to basically apply that to simulated data so that we understand what's the meaning of each. Okay, so at least we know the differences and see the differences, and we can actually simulate different samples so that we can see whether the whether what we have makes sense or not. So what I'm going to do now is basically start with simulating some data. Okay, so basically we're going to talk about statistical analysis. Okay, so basically I'm going to simulate two sets of signals. I'm going to make the signals very simple so that you can understand them. Okay, so basically I'm going to simulate a sinusoidal. It looks like this, and another sinusoidal that looks like this. Different frequencies, F1, F2. We did that already in the first part of this course. You know how to do that. But actually, if you want to have sets like the ones we have, the ECG signals we don't have only one signal. We have many signals. We have like 64 signals for training. So I would like to simulate many signals with the same frequency. Okay, but actually, if I simulate them just like what we did before, you're just going to get the same exact waveform because it's exactly the same equation, right? It's not going to differ between different, you know, if you use it 100 times, each time I'm going to get exactly the same looking signal. The thing that I basically expect to see in real life is that I don't usually start from the same point. So this starting point here will differ because basically whenever I start sampling, basically will be different between different patients. So basically you're going to get different phases this sinusoidal wave, right? Different phases, so that basically we will have a set of signals that have the same frequency, but actually they have different phase. This is what we will see in ECG. The same thing here. I'm going to simulate basically same frequency, but basically for both we have random phase, so that we can see, you know, differences that actually are expected to be present in real life signals. So let's do that. I'm just going to simulate two sets of signals with each one having the same frequency, the random phase. Okay. So let's call this link 7. Oops. Okay. So I'm going to simulate two sets of signals, sinusoidal, with different frequencies. And random phase. So basically, let's make it a little bit general. I have for each signal number of points. Let's make it like 100. Let's make it exactly the same as the one in our problem. So basically, this is the length or number of samples in each signal. And I'm going to say that maybe the number of samples for each one of the signals. So basically I have two types with two different frequencies. So basically let's say that we're going to take 10 signals for each. Maybe type means set so that I can use the same exact terminology. So I'm going to just generate it the way that I did before. Let's put F sampling. It's 360. This is sampling frequency. This means that TS is equal to 1 over Fs. You're going to need that to basically generate the samples. F1, let's make it similar to ECG. It's around 1 Hertz. F2, probably consider something that is much higher, so that we can consider something like ventricular fibrillation, for example. Let's make it 5. It's very different. It's something different. So basically, this is frequency for set number 2. Okay. As we did before, just make n equal to from 0 to n. NP minus 1. This is the time variable or the discrete time. So we're going to generate the signals as sine, as we did before, sine twice pi times F1 or F2, whatever, times n times Ts, as we did before. Remember? So let's generate. Yeah, go ahead if you have a question. Have a question? Okay, let's continue. I actually need to generate 10 samples or 10 signals, each one having a number of samples like this. Okay, so let's put this, or basically generate arrays so that we can put the data in them. So basically, I'm going to have these as zeros of NS and NP. This will generate an array of NS times NP so that I can store the data in it. I'm going to have the second one, the second type is signal 2. Okay. So for K1 equals to 1 to NS, I'm going to generate in signals. For the first one, signal 1 of K1 and everything will be equal to this. And you following what I'm doing, or you have any problems? I'm just trying to generate multiple signals that are stored in arrays, signal 1 and signal 2. Is that clear to you? Here I'm generating for k equal to 1, k1 equal to 1, I'm going to generate one signal and store it in the position 1, and then 2, then 3, then 4, and so on. Okay. Here I didn't put the phase. I should put the phase here, but actually I'm just going to show it to you without the phase. After I do that, I generated a set of signals with frequency F1 that are stored in sig1. Here I basically generated a sinusoidal signal, a set of sinusoidal signals with frequency F2 that were stored in sig2. I'm going to plot them. There's a very nice thing in plots. When you have a two-dimensional array, you can actually make MATLAB basically plot all of them, superimpose, having to do that yourself. So let me show it to you. Here I have the signal is basically NS times NP. If I basically use S1, basically if I say that, I should have subplot first. I plot the two signals, plot sig1, let's see what's going to come out of that. It's not going to be correct like this, but actually let me show it to you first. Let us close all first, so that Usually it's better actually to start with close all so that you don't have any open figures. Does this make any sense to you? It actually looks very strange, right? So basically, actually, what you're supposed to do in order for MATLAB to do that properly, just transpose that. Just transpose it. Transposing means that instead of the samples or the array being ns times nb, it's going to be np by ns. So basically, I'm moving the samples to be basically in the first dimension of the array. Let's see what's going to come out of this. Actually, they were all drawn here, basically superimposed on each other. If I wanted to see the signals without that superposition, basically I'm just gonna add here a phase of K1. If I add a phase of K1, it means that for the first signal, I'm going to have a phase of 1, then 2, then 3. Remember that whatever is inside the sine wave is basically considered in radians. So 1 would be like almost 1/1/3. So it's about maybe 60 degrees, something like that. 2 is going to be like 120 degrees. Let's see it like that. See now? Basically, you have a set of signals, 10 signals, basically the one that we generated, but actually they are separated or they are basically having different phases. But actually, I'm afraid that if we use a regular phase difference like this, it might not be actually a good reflection of what we expect from reality. Because in reality, you usually have basically random phase. So we need to basically generate a set of signals with random phase here. How can we generate a random phase? If we go to MATLAB, there is a function, a very interesting function called rand_n. Rand_n is a random number generator, basically. Generates normally distributed pseudo-random numbers, okay? If you use rand, just rand actually gives you uniform samples. So here it gives you uniformly distributed or normally distributed pseudo-random numbers, basically using a distribution that has 0 mean and 1 standard deviation. So let me show it to you basically, if I'm talking about rand_n in MATLAB. It considers a Gaussian distribution, normal distribution basically. The normal distribution has a 0 mean and a standard deviation of 1. So can you tell me the approximate range of the values here? Basically, imagine that for realistic considerations, we say that if you are mean plus minus 3 sigma, you consider that this is almost 99% of the range of the Gaussian distribution. Okay, so basically, if you go to here, 3 and minus 3, you have almost 99% of the curve. The remaining part here and here can be very small. It accounts only to 1%. So basically, I expect the numbers to be between minus 3 and 3, which is almost pi and minus pi in pi. Okay. So if I wanted to change that, if I multiply the distribution, if I multiply the numbers by 2, for example, then the 2 will multiply also the standard deviation. If I have a distribution with a standard deviation, sigma, okay? If I multiply the number by 2, then the standard deviation will come out like 2 sigma. If I multiply any number here, the standard deviation will be multiplied by the same number. So if I wanted to generate numbers from, for example, minus 6 to 6, then I have to multiply the random numbers by 2. Okay, let's try that. So here, instead of putting K1, I'll leave that also so that you can remember that we did it. Okay, let me also put the original one that we did before. Put a comment here. Identical signals, which are useless. Phase with regular change, not like reality. Not sure that's okay, that's fine. Not realistic. So I'll comment that. Okay. Now I'm going to replace that with rand n. Rand n actually all it asks for the argument, the only argument that you have here is the number that you have. Basically, if you have just one number, it's going to give you n by n matrix. Okay. So if I put here 1, then it will give me a random number, just random number. If I say rand n of 1, it's going to give you a number. Each time you basically call this function, it's going to give you a random number. That's it. So basically, if I put it inside rand n of 1 here and rand n of 1 here, basically it's going to give me a different phase for each one of these. Let's try that. See now? But actually, if you notice that the numbers usually, because of the distribution here, is actually concentrated around the 0. So basically, the phase range here wasn't really very good. The figure here, the phase variations are concentrated near the 0. Okay, so I wanted them to be distributed a little bit better. So basically, if I come to the value that comes out and multiply by 2, basically I increase the range around 0. So if I do that, you're going to get something that looks a little bit better. So the phase is a little bit more distributed. See here, for example, it's a little bit more distributed than here, basically. And both of them are more distributed than before. They have a wider range. Okay. So now we have a set of signals. Basically, these are 10 signals here and 10 signals there. They are superimposed on each other so that we can see them. Obviously, this is a different class from this one here. This is a class of signals with a frequency of 1 Hertz. This is a class of signals with a frequency of 5 Hertz. How can we discriminate between these two? Basically, if I try to compare them directly, it doesn't make sense, because basically, even if I directly compare one signal to another within this class, it will not compare well, because basically they started at different points. So imagine that you have this one here with the one that started from here. They are very different. Basically, you have here a peak, you have here almost a valley. So they are completely different. So you cannot directly compare them. What we can do is to think about what we call statistical features. Statistical features basically are numbers that represent this particular signal. What does that mean? Okay, let me give you a general definition for a feature and then basically apply that general definition to whatever we're going to do. Okay, statistical feature. It's by definition a function of samples. What does that mean? Basically, you combine the samples any way you want, and this will basically become a statistical feature. Like, for example, the mean. But how can you compute the mean? If I take the samples, summation of the samples, okay, and basically divide them by the number of samples, this will be basically a feature. Same for the standard deviation. Okay, you can basically consider all the statistical features that you learned from before, and basically they are all will apply here. The variance, which is basically the square of the standard deviation, is also a feature. You can consider anything that you can combine the values within the samples and come up with a number. This will become a feature. Okay. So let's consider these very simple features. Let's consider the mean and the standard deviation, because actually these are dependent. Basically, this is the square of this. So basically, they are not really. Doesn't make sense to basically talk about the variance by itself. So basically, you can either consider this or that. Let's see these and see whether they will give us something that can be used to characterize the signals or not. So how can we do that? Basically, we have a function in MATLAB. Very simple function. If you have an array here, it will give you the average. That's it. But now we have an array that contains arrays. Yeah, basically, I have each column in my array, or each row actually in the type of array that we created. Each row represents a signal. I would like to basically compute the average for each one of the signals by itself. How can we do that? Actually, if you have an array that is n-dimensional, the mean is applied to the first dimension. So it means that if I have an array here, for example, the one that we created, signal 1, if I apply to signal 1, I basically am going to average over the first dimension, and basically the result will come out like 1,000 or 1,080 means. Do I do that? Do I want to do that? Actually, I want to do the opposite. I would like to average 1080 and basically come up with 10 means, one for each signal. So basically, all I have to do is just compute the mean of signal 1, signal 1 transpose. So mean of sig1 by itself is not going to work because it's going to give me, basically, it's averaging across samples. I don't want to do that. All I want to do is basically average for each sample. So this is the average 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 samples or 10 means. This is the mean for signal 1. Basically, if you consider the figure here, you have several signals. Each one of these signals will have a mean value that came out from this particular equation. Okay, so now I computed the mean. Same thing I can do for the standard deviation. Standard deviation, I have a function called STD. Okay? Same thing, sig1. I do sig1 is going to give me 1080, the same thing. Basically, I have to do it exactly the same way. Now I have the standard deviation values like that. Okay. So let's see that. Let's try and see the values, the mean and the standard deviation, and basically try to plot them, so that we see whether they are basically they are useful to discriminate between the two types of signals or not. Okay, so what I'm going to do is have mean 1 is equal to mean of sig1 dash. So basically here I'm going to talk about features. Sig1 dash and mean 2 going to be equal to mean of sig2 dash, and basically let's plot them so that we can see how they look like. Okay, because actually it's useful to see how the samples would look like. Okay, so maybe I can have a plot, a new plot, figure 2, and And because actually here I'm going to get a set of means, I can just draw them with the n. So basically I can do it this way. I would like also to plot them with basically the first means will be like in circles, drawn in circles, and the other one in X's, for example, so that I can see the difference between them and in different colors. So I'm going to have plots so that I can do it the right way. Maybe I can just do it this way. M1, maybe I can have it like XB, X meaning that it's going to be drawn in X's, and B is going to be blue, mean to maybe O, R, like it's going to be circles and basically okay. So let's see how that looks. Okay, didn't work. Okay, I have to have X and Y then. If I want to have more than one signal, so I'll just have X as, because the length here is NS, so I'm going to have one NS here. One NS here, because actually if you want to draw more than one signal in plot, you have to have XY, then options, XY options. So I didn't have X before, so I added X now. X is basically the number of samples, just the array of the samples. Okay, how do you like that? The circles and the X's are like that, like what you see here. Basically, circle, circle, circle. It's actually very difficult to see actually whether they are separated or not. But actually, we can see that it's very difficult to separate the circles from the X's. What we can do is probably increase the number of samples here to 100 so that we can see it a bit more. How do you like it this way? Can you see a separation between the X's and the circles? Can you see that basically one sample or one type of samples can be discriminated from the other based on something like this? Actually, there is no basically, if you look at these, it's all over the place. Basically, you have the values basically anywhere you can expect to have either basically the chances of being a circle or an X is probably the same. Okay, so basically, it doesn't seem like this will be a useful feature to use, which makes sense because the signals we use actually both have a mean of 0. The theoretical signals basically we use, both are sinusoidal signals. See here, when we have many signals, basically each one of them is expected to have a mean of 0. What we're getting here is basically makes sense. The mean is not discriminating here. It's not going to be possible to use to discriminate between these signals because basically the signals here and the signals there do not have differences in terms of their mean. The mean is exactly the same because they are both sinusoidal signals. The only difference is in frequency. So the mean didn't discriminate that. Let's try it with the standard deviation. Let's try to add the standard deviation and see. Okay, so we're going to copy these. Okay, maybe you can have it the same figure. And I have here standard deviation. Let's call it S1, S2, and this is STD. So I'm going to draw now the two other signals. This here S1, here S2. Let's see if this will make a difference. Okay, they are almost identical here. Basically, see each circle has an X inside. Okay, so basically these are useless. Basically, if you're trying to guess which signal type you have, and basically try to do that using the mean or the standard deviation, you have no chance, basically. So what can we do? Maybe what we can do is try to use some more elaborate features. Maybe basically the mean might not be very useful, but actually let's consider how the shape of the signal looks like here. And basically we expect, because actually this has a lower frequency, if you try to compute the slope here, so the derivative of the signal, if you consider the derivative of the signal, because here we have so many variations and we have very steep or steeper lines here, maybe the differentiation will actually give us something that would be more useful. So there's a function in MATLAB that differentiates digital samples called diff. Basically, it basically computes the difference, and basically it's the approximation of derivative for digital signal. So what I'm going to do here is instead of using just the mean, I'm going to add here differentiation, but let us just keep it let's keep the first set so that we know what we did, or at least when you review the code, you will know where we were. So what I'm going to do here is just add diff. If it's exactly the same, it applies also to the first dimension. So let's try here if we add diff and see what happens. Basically, the process of trying to come up with features that represent differences between different types of signals, basically it goes like this. You see something basic, try it, and basically it doesn't work, try to make it a little bit different and try again. This is what we're going to do. How about that? Actually, this is perfect. See that the standard deviation now, it's perfect. It's actually very good. It looks actually extremely good. Here, it's actually not bad also. Basically, if you see that the x's are in the middle here, near zero. The O's are basically outside. So basically, if you are in the middle here near zero, you can actually think if you have a line here, you can actually contain all the x's and basically have most of the O's outside of it. So actually here, it's not bad. It's not bad at all, actually. Okay, so actually, yeah, a very simple change we made resulted in very good results like what we see here. Let's think about something a little bit more. Remember the difference, because when we have a difference, we have a slope, positive slope and negative slope. So maybe what we can do, because the mean actually doesn't basically doesn't account for the positive and negative, basically it cancels out positive and negative. Maybe what we can do here is just take the absolute value of the difference, or absolute value of the derivative. So basically, if you have a slope that is positive 1 or negative 1, they will be added because they will be both 1. Before, 1 plus 1 would be 0. So let's try the absolute value also here. The standard deviation doesn't matter because I square the samples. So it doesn't matter. Let's try that. Ah, that's very good, actually. See now? Big difference. So all these have variations, by the way. If I try to zoom in, I can just try it here. No. always have variations, but actually they do not see how they vary. They actually still vary. See, they are not the same value, but actually they are very close together. Okay, if you go back, you think that they are almost the same value, but actually, if you do it this way, it's very clear that basically you can basically look at the value of this feature. We call it feature now because we computed that from the samples. You can put a line in the middle here and say that if we are above this line, it will be sample 2. If we are below, we are sample 1. And this is very, very good actually. This is much better than the ones we started with. So this is exactly what we're going to do in ECG. We're going to try to do that. We're going to try to find features that are computed from the samples, the values of the samples, and basically try to make sure that they are different between the different types. If they are not different, if they are like the ones we saw before, like they are overlapped together, then basically we cannot do much. Basically, they are not discriminative. They do not discriminate between the different types. Like basically, if I'm talking about ECG or basically heart patients, and I'm going to take features that include the color of the eye. Okay, I always give that example because it's a very representative example. The color of the eye is a very important feature for a person, of course. But is it relevant to the problem of ECG classification? Is it relevant to the problem of diagnosis of a heart condition? No, it's not. This is exactly the same as what we're talking about here. If the feature corresponds to the condition, changes with the condition, then it's very representative, it's very useful. If it's random, almost random, it changes all over the place, it doesn't really have a specialized range for each condition, then we cannot use it to basically identify these conditions. Okay? Is that clear?
Yes, clear.
Okay. So now, do you understand the idea behind features? These are not the features we're going to use. Basically, maybe we can use them, but we're going to actually discuss how to actually do more features. Maybe I can give you some ideas about other features. So basically, one of the features that we're going to use is something that we did before. Remember that discrete Fourier transformation? Discrete Fourier transformation will give you the spectrum, right? Each point in the spectrum is a feature. Because basically each point in the spectrum will basically represent something that looks like this, a function of the samples. Okay, and actually it's very useful. You can think about it like if you have ventricular fibrillation, for example, the high frequencies will be high for ventricular fibrillation than the normal. So you would expect them to be actually very useful as well. So basically, the DFT, if you remember, if we have a 1080 sample vector and do DFT, FFT, whatever, you'll come up with 1080 values, right? Because of the symmetry, basically, you will end up with half of that that are unique. But each one of these will basically be a feature. You can use it as a feature. When I talk about you can use it, you don't have to use it. You basically try to compute as many features as you want, as you can, okay, and then test them. Try to see whether the feature is representative or not. Representative means that, or discriminative, it means that it gives you something that's close to this. This is close to this. This is actually ideal. This is not expected, in realistic conditions, okay? But actually, this would be an ideal situation that we should shoot for. If you came up with something like that looks, like the ones we got before, then it might not be used. Okay? So the idea is we're going to propose several ideas for features, and we're going to compute them, and then we're going to have to filter them, meaning that I'm going to have to select a few of them that are most useful. Some sometimes when you look at the features in a graph like this, it might not be very useful to, or might not be possible actually for you to discriminate or say that whether this feature would be useful or not. You have to come up with a more rigorous method of selecting the features, or basically saying that whether the features are useful or not. Basically, this is done through something called statistical testing or statistical hypothesis testing. This is the next topic we're going to talk about. Basically, statistical hypothesis basically what we're going to do is we have two hypotheses, H0 and H1. Hypothesis H0 and H1, you're talking about you have two samples. You have two data sets. Okay, you have like what we have right now. Okay, you have data set 1 and you have set 2. Okay, what you would like to do is, this is, for example, let me to be specific so that you can understand what we're talking about. This is, for example, the mean for set 1. This is the mean for set 2. Okay. The statistical hypothesis testing tests two hypotheses. The first is whether the means are the same or the means are different. If you have, ideally, if you look at the ones that we have here, basically the mean of these features, the mean of these means would be something that is around, for example, 0.055. Here it's going to be close to 0.01. They're both different. So the means here apparently or clearly that are very different. I want to have that. I want to make sure that, or at least ensure that for a useful feature that the means are basically different. If they are not different, then basically the samples will overlap. Basically, I cannot separate them. Okay. So basically, if I ensure that H1 is the case, okay, then I can say that these are actually these two sets came from different distributions. So basically, this is called usually the null hypothesis. Null hypothesis. Okay, meaning that the samples do not have any difference, meaning that these two sets do not discriminate, between the two sets. Basically, these samples and those samples they virtually came from the same set, from the same distribution. Okay, so in order for us to do that, basically, let's try to simulate now two distributions. Two random distributions. With different means. Okay. And try to apply the testing, this way and see what's going to happen. The thing that does that in MATLAB is something called t-test. Okay, the function MATLAB is t-test2. T-test2 is basically, if I'm comparing two samples like this, two sets of samples like this, basically the function is t-test2. What comes out of t-test2 is two things. It gives you whether you have H0 or H1, and gives you what's called the p-value. P-value is basically the chance of H0. So basically, p-value is a probability of H0. So basically, if I wanted to have H1, if I wanted to make sure that I am at H1 is the proper hypothesis, this is the correct one, or this is the the hypothesis that applies to my data, I have to make sure that the p-value is very small. Usually, people like to have it below 0.05. It's very small. Okay, if it's above that, you cannot rule out H0. Okay, so basically, if the p-value is below 0.01, 0.05, it will give you H1. If it's above 0.05, it's going to give you H0. Okay, so let's try to simulate that and see what happens. In order to simulate two random distributions, I'm going to use exactly the same rand-n function that I used before. But actually, instead of just simulating one sample, I'm going to simulate basically a set of samples. So let's try here. Hypothesis. Okay. So let's have x1 and x2, for example. x1 is equal to rand n of let's have a number of samples. Maybe let's just use a number of samples above, number of points above, and 1. If I use NP, it's going to give me an array of NP times NP. I want to have an array of NP times 1. Okay? And x2 is equal to rand n of NP1 and 1 also. Remember that if you call the same function twice, it's going to give you different numbers. This is random number generators. Basically, you're never going to get the same number twice. Okay? Let's plot these just to see what the samples look like. Okay, figure 4.3. Here x1, and I don't need the second one. I don't need actually to have a subplot, just one plot. So here x1 and x2. Oh, here I have to have it NP, not NS, because I have number of samples as NP. See how these look like. How do you like that? Basically, they are both having the same mean and the same standard deviation. Let's try to see if the t-test will detect that. T-test is written like this: h and p, basically any variables you want, equal to t-test2 of x1 and x2. That's it. Okay. H is 0 now. P is 0.8957. This is really large. Really large. I mean, it's definitely above 0.05. So basically, it's hypothesis 0 now. Basically, you cannot rule out, or basically, both data sets came from the same distribution. They have the same mean, which is actually the thing that we did. The useful thing about simulating data is that we can go back here and add a mean value. Let's just put here maybe put M1 equal to, or put the number right away. I'll put here, for example, for the second distribution here, I'll put here 1. Okay? When I put here 1, all the values that came out of here will be added to 1. Remember that when we have a random number, or basically a distribution, random numbers from a certain distribution, if you add a constant to the value of the random numbers, it will effectively change the mean by the same value. So let's see how that looks like after we basically do that. Basically, you see here, they are overlapped, completely overlapped here, okay? Let's choose the number a little bit large so that we can see a difference. So I have now added 3 to the second one. Let's see how the outcome will look like. See now the difference? Now the samples from the second random numbers are now, their mean is 3 now. So they are different from the original sample. The original samples in 1 that have a mean of 0. So let's try now to see here, H is 1, the probability is almost 0, almost 0. Okay? It's actually MATLAB doesn't read if you have a very small number. Usually, if it's close to 0, then it approximates it to 0. So basically, you have a 0 probability that means are equal. So here you're sure that basically the means of the two distributions are equal. Basically, we need to do that because we need to do the same thing for the parameters or the feature that we get. If I have a vector with the features from the first class of ECG signals and another vector for the second class, I would like to make sure that there is a difference in their mean. If there is a difference in their mean, then it means that this feature can actually discriminate between the two cases. Otherwise, it will not. Let's see how far we can actually still detect the difference in mean. Okay, so now I'm going to have that as 1. So let's see if it can detect it or not. 1, you see now there is an overlap. There is more overlap here because the mean now is at 1, not at 3. Let's see now. See now the p-value has a value. It's still detected that the mean is different, but actually the p-value now became a little bit larger, but it's very small, but it's still there. Let's try to make it a little bit smaller, 0.1. See now, they are very, a lot of overlap here. See now, it's now, you still have a difference because actually the means are still different, but the p-value now became much larger than here. Let's go back and do a little bit, make it a little bit smaller and see. Now it's almost like the first case. Now it's not. When the means became too close together, actually it was not able to detect that mean difference between the two cases. Okay, so basically the t-test, the hypothesis testing would help you very much. Like if there is a significant difference between the means, then it will detect it and tells you that. Okay, so one important thing to take into account is that the number of samples here will make a difference. So let's, for example, have this back as 0.1. 0.1 was still detectable. The difference was still detectable here. Okay, it's 0.0016. Let's make the number of points here half. So I'm simulating now. Maybe I can change the NP because actually, don't do that, it's not going to plot right. Just put NP here equals to, instead of 1080, I'm going to just have 100 samples. 100 samples will be much less like this. See now, here, the only difference between these two is the number of samples. So that's why you can discriminate more when you have more cases. Okay, so when I try to do a diagnostic system, and this diagnostic system was based on 10 patients, it's going to be really difficult to discriminate, if you have a small difference between the different cases, the different diseases. If you have 100 cases, then you have more. You can actually detect a little bit more differences. Okay, here let's see the 100. Let's see how much difference we need here in order for you to be able to detect. Let's just put this as 1 and see whether it can detect it or not. Actually, 1, it's okay now. Now it detected now that there's a difference. But actually, for the 0.1, it couldn't. Maybe 0.5 also, it will not. Let's just try this 0.5. Actually still okay, but actually you notice that we are 0.01 now. It's not very far from 0.05. So you are critical here. So the more samples or the more cases, the more signals you have for each case will help you discriminate between a particular disease and another. This is the effect of sample that I would like you to basically notice. Okay, so what we're going to do now is basically apply the same idea here to the mean and the standard deviation that we got from here. So basically, I'm going to apply this now to the sample that I have here, the mean and the standard deviations from here. Okay, so basically apply to features. Okay, so I'm going to take that here now. M1 and M2, and maybe S1 and S2 as well. Let's try that and see. This is mean of derivatives, absolute derivatives. And standard deviation of derivative, that's just derivative. So now here, it's very clear that both are discriminating. Actually, it's very clear from this figure, but actually we got that from the result here. I don't have to look at each feature by myself. Okay, imagine that you're going to generate like what we're saying just with FFT. You're going to have hundreds of features. You don't want to do that. You don't want to do that manually. You want to have a computational method that you can use to compute a figure, and you look at this figure and basically decide whether this feature is useful. Let's try that with the mean. Okay, just the mean and the standard deviation, the original ones. Or basically, instead of having that, I'm just going to have this, the mean of the derivative. I'm just going to remove the absolute value here that made the mean very useful. So I'm just going to use the derivative, the one that give us something that is a little bit more overlapping. Basically, this is the case here. We have overlap here. So now here, see now it's 0, and the p-value is 0.1. 0.1 is above 0.05. So now this is not useful. This is useful. Okay. So this is basically the basis for feature selection. What we're going to do is continue to basically compute features of different equations, different origin, like frequency domain, like more statistical features like entropy, like contrast. There are so many different features that we're going to discuss inshallah next time. And for each one, we're going to compute the p-value. And basically, based on the p-value or based on the h here, we can discriminate whether this feature is useful or not. So this is basically the idea behind the feature selection. Is that clear? So the idea basically, let me just write it down for you. Test the hypothesis. Actually, people actually in the statistics just call t-test the null hypothesis, because actually it's very well known for each feature. For each feature of different cases, for different diseases. So basically, if I have this feature, feature 1, for example, okay, I will have an array, okay, for normal and another array for abnormal, for example. I basically compare them using t-test2. And basically, I'm going to get H and P. Okay, some people look at H, but actually I prefer to look at P, because actually for the P, the smaller we get, the better. So basically, take this as the metric. Basically, measure of goodness of each. Okay, of course, smaller, the better. Okay, so this is basically going to be the way we're going to do feature selection in our project, inshallah. I think I should stop at this point here. I've just asked you about if you have any questions, and inshallah next time I'm going to talk about the idea of classification and get started on trying to compute the features. Just going to propose a few features and basically do this kind of feature testing or feature selection based on the ECG, the actual ECG signals. So if you have any questions, please let me know now, and if not, we're going to conclude this lecture, inshallah. Any questions? Okay then, so yeah, go ahead.
Thank you, Professor.
Okay, thank you. So inshallah, we'll meet next time. If you have any questions related to the assignment 2, please send them to me during the week. Do not wait for the next lecture, and don't worry about the time. Take your time to finish your assignments. Okay, and for those who submitted with, I had some comments on them. Please resubmit anytime. Okay, the most important thing is to understand my comments. And if you resubmit, you're not going to get like a deduction in points or anything like that. As long as you did the things properly, you get the marks for them. Okay, as long as you understand them. So basically, if you submit something, and you can submit whatever you think, and basically, if I have an issue or a problem with something, I will let you know so that you can correct it. So don't worry about making sure that everything will be perfect before you submit. Okay.
Okay.
So I'll see you inshallah next Friday, inshallah, bismillah. Thank you very much. Assalamu alaikum.
Inshallah.